We now discuss the topic of implicit differentiation. Now, implicit differentiation is essentially an extension of the chain rule. We need to understand how to distinguish between implicit functions and explicit functions. Up to this point, we've only dealt with what we call explicit functions or functions in explicit form. And what we mean by that is that functions are essentially solved for y. So you have these y equals or f of x equals functions. In which case we say that that is solved explicitly for y, or y is explicitly written as a function of x. So this is an explicit function. So up to this point, we've only really done explicit differentiation. But not every function or equation is written in explicit form, y equals, okay, or f of x equals. Some functions are implied, and they're written in implicit form. In this case, x times y equals 1. That's an implicit equation. That's not a y equals equation. Now we can easily get it into y equals form. I could just write this as y equals 1 over x. In that case, now we can put it in explicit form. But sometimes it's not that simple. Here's another one. X squared minus 2y cubed plus 4y equals 2. That's an implicit equation. And we can't easily get that into explicit form. However, if we were to graph this, this would represent some curve. This explicit equation would represent some curve. And we may need to find the slope of that curve at different locations. And so we would want to find the derivative of y with respect to x. Now, when we have the y equals, or the explicit form, so say y equals 3x plus 2, we can take the derivative and find dy dx very easily by taking the derivative of both sides of the equation, okay? Primarily, we focus on the right-hand side, but we really are taking the derivative of both sides. When you take the derivative of the left-hand side of the equation, you're taking the derivative of y with respect to x. And we could write dy dx, or we could write y prime, but either way, that's taking the derivative of this side of the equation. Then we take the derivative of the right side of the equation, and we would get 3 in this case. Very simple. But we could figure out what y prime equals, or what dy dx equals, very easily when we have an explicit equation. That's a little trickier when we have an implicit equation. So what we're going to have to do is we're going to have to learn how to do implicit differentiation, how to find dy dx for an implicit equation. Now, there's a couple of ways to go about this. In this video, I'm going to give you the most traditional way of doing this in a Calculus 1 course. There are some other ways to do that, and I will not cover that in this video. So what we're going to do is we're basically going to be using the chain rule, okay? And we're going to be treating y as a function of x, and we're going to apply the chain rule to that function of x, and thinking of this as inside and outside function, like we do with the chain rule. So to see how this is going to work, let's look at a couple of expressions first. Rather than look at a full-on equation that's in implicit form, let's look at a couple of expressions and think about how we would take the derivative with respect to x for each of these expressions. And that'll give you an idea of how we're going to do it for a full equation. So let's look at this first one. So in this first one here, we have the derivative with respect to x of x to the fourth. Now here, this is just like something we've been doing now for a while. This is a x expression, x to the fourth. We're taking the derivative with respect to x. And so what we would do here is just use our simple power rule and say that this is going to be 4x cubed. The variable I'm taking the derivative with respect to and the variable in this expression are exactly the same. It's x. And so this is just our simple old, basically explicit differentiation. However, let's look at the next one. And this next one, we're taking the derivative with respect to x of y to the fourth. Now here the variable is different, and this is where we get into the implicit component of this thing. So what we're going to do is we're going to treat y as a function of x, which it is, okay? But think of it as a function of x that you don't know. So you could write y to the fourth as, say, some function of x to the fourth. And think of this as inside function, outside function, okay? So whether I write f of x to the fourth like this, or whether I write y to the fourth, they're the same thing because we know y and f of x are interchangeable. So then think of this y as some inside function, okay? And this fourth power is the outside function. And so if we were to do that, when we take this derivative, we would do the outside component first, okay? Do that power rule essentially first. The 4 comes out, the new power is 3. The inside function would stay the same, and then we would multiply by the derivative of the inside. Well, the derivative of that inside function is the derivative of y with respect to x, or dy dx. Or you could write y prime. I don't particularly care for writing y prime. I think that starts to cause errors when students are doing this over a full equation, because this could start to look like a first power, and this is a 3, and then I see all kinds of issues there. So I prefer that students write dy dx, the derivative of y with respect to x. That's a derivative of this, okay? And so that's the implicit way of taking the derivative here, and this is explicit. And the difference is, and let's erase a little bit here so you can see it. The difference is these variables were the same and these variables were different. That's why we needed explicit differentiation here and implicit differentiation here. So you see it starts off very similar, okay? But this is the difference. All right, let's look at this next one here. I'll bring it down here. So if I want to take the derivative with respect to x of this whole thing, well, all our derivative rules still apply. So this is a sum. So what I'm going to do is I'm going to take the derivative with respect to x of x squared plus the derivative with respect to x of y squared. Now, in taking the derivative with respect to of x squared, it's a lot like this first one, and I would just get 2x. Plus, if I want to take the derivative with respect to x of y squared, that's a lot like this one here, and I would think of it as the power part first, and the inside function stays the same. And then, since this is implicit, because these variables are not the same, I would multiply by the derivative of the inside, the derivative of y with respect to x. And so this would be the derivative with respect to x of this entire expression. Okay, we have one more to go. Let's bring this one, let's just change colors. Let's bring this one over to here. Okay, so we want to take the derivative with respect to x of this entire thing. But you see, this is a product. Just like this was a sum and we used the sum rule, this is a product and we have to use the product rule. What I'm going to do here is rewrite this again in a bigger spot so I have more room. 3xy cubed. What I'm going to do here is I'm going to group this as this is the first function and this is the second function, and that's my product. Because technically this 3, I could pull all the way outside as a constant multiple, but then I have to put it back in later. And I don't like to have to distribute it later. So if I just leave it with the x, then I don't have to worry about the distribution later. So anyway, 3x is the first function, y cubed is the second function. So if I was to take the derivative of this, I would have to take the derivative with respect to x of the 3x, then multiply that by y cubed, plus 3x times the derivative with respect to x of the y cubed. And in doing that, I have to take the derivative here and here, This would be explicit differentiation because the variables are the same. And I would get just simply 3, and that would be times the y cubed, plus here I have 3x times this derivative. Now here's going to be your implicit differentiation. So I'm going to get 3y squared. That's the power part. That's the derivative of the outside. This inside function here will stay the same. And then I'm going to multiply that by the derivative of the inside, dy dx. And there is my derivative of that entire expression. I would be using the product rule. I could simplify this, obviously, from here, which I would, but that's the derivative. So I would have 3y cubed plus this would be 9x y squared dy dx. All right, now that you have an idea of how to do it for these individual expressions, we can then go after a full equation that'll contain expressions like this. So, basic guidelines for implicit differentiation of an implicit equation. Okay, and again, you got to recognize the difference between an implicit equation and an explicit equation and when we would need to do this. And I think that's one of the issues that I see students have the most when we first look at implicit differentiation is recognizing when and why we need to do it. So explicit equation versus implicit equation. First off, if you're doing implicit differentiation, you're going to want to differentiate both sides of the equation with respect to x, which is what we've been doing all along. Again, we've been mainly focusing on the right side of the equation because it was y equals, and the left side would just be y prime. But we were taking the derivative of both sides of the equation ever since we started derivatives. Next, collect all the terms that involve a dy dx on the left side of the equation, and then move all the other terms to the right side. And you'll see this happening in this example. So we want to start grouping together all the dy dx terms and move everything else to the other side. Once we have that, we're going to factor the dy dx terms out of all those terms on the left-hand side. Finally, solve for dy dx, and you have the derivative, what dy dx equals. So here is an implicit equation. Okay. It's not a y equals equation. It's an implicit equation. So what are we going to do? What we're going to do here is we're going to take the derivative with respect to x of both sides of the equation. So it's x cubed plus y squared minus 5x squared y, and the derivative with respect to x of negative 4. Okay? Then what I'm going to do is start applying my derivative rules, actually do these derivatives. So what do we have? We have a sum and a difference here, so this derivative can be split apart here, here, and here separately. So I could do the derivative with respect to x of x cubed plus the derivative with respect to x of y squared minus the derivative with respect to x of 5x squared y. And on the other side, I have the derivative with respect to x of negative 4 still. I didn't do that yet. And the more of these you do, the faster you'll get through this. You won't have to write necessarily every one of these little steps down. But it's good to do that at first. And so look at this. Each one of these derivatives looks like those expressions we just got done talking about. And so if we can do each one of these, we can continue, and we can. So the first one, derivative with respect to x of x cubed. It's an explicit derivative. Variables are the same, so 3x squared. That's it. Done. Next one. This is implicit because it's y, but we're doing it with respect to x. So 2y, then dy dx. Minus the next one is a product, just like that previous example. What I'm going to do is I'm going to attach the negative in here with the 5 so I don't have to distribute it later. So I'll have the derivative of the 5x squared. So that's going to give me negative 10x. That'll be times the y. Again, I attached the negative in there. And then still the negative will be in there with the negative 5x squared. And then I have to take the derivative of the next piece, which is the y. And that'll be dy dx. That's how you take the derivative of y. So that whole piece right there is the product rule for this function. And then on the other side, it's the derivative with respect to x of -4. It's the derivative of a constant. That's always going to be 0. And so what you notice is that this term has a dy dx in it, and this term has a dy dx in it. So I'm going to put those together, group them together. These other two terms don't have a dy dx, so I'm going to loop them to the other side of the equation. So I have 2y dy dx minus 5x squared dy dx equals minus 3x squared plus 10xy. Then I can factor the dy dx out of these two terms. Dy dx times 2y minus 5x squared equals negative 3x squared plus 10xy. And then finally, I can get dy dx by itself by dividing this to the other side of the equation. And I ran out of room here, so I'm going to tuck it up here, and I get dy dx equals negative 3x squared plus 10xy divided by 2y minus 5x squared. And that's your derivative. Okay? And we did that implicitly. So, the big takeaway here is all your rules of derivatives are still going to follow the same. Sum and difference rule, product rule, quotient rule, etc. When you're taking the derivative of something that only has x in it, it's explicit. If you're taking the derivative of something with y in it, that's the implicit part. And you treat y as an inner function. And essentially, you're always going to have to multiply by a dy dx, which will always be the derivative of the inside component. So knowing your derivative rules, like this piece here, knowing the product rule will help you get through this better. The less confident you are in your derivative rules that we've learned so far, the harder this is going to be. So you really should have your derivative rules that we've learned up to this point down to be able to be successful with this implicit component to it. So here's another example. Determine the slope of the tangent line to the graph of x squared plus y squared equals 1 at the point square root of 2 over 2, comma, square root of 2 over 2. Now, we should all know that x squared plus y squared equals 1 is the unit circle. Here's your graph of your unit circle. Square root of 2 over 2 is the point that the 45-degree line goes through, so that point is right here. So clearly, this function, this graph of this equation has a slope right here, okay? And therefore has a tangent line that has the same slope as the equation does right there. And this question wants you to find the slope of the tangent line. But remember, the slope of the tangent line and the slope of the graph of that equation are exactly the same. And what is it? It's basically asking you to find dy dx. That's what the slope of the tangent line is. But this is an implicit equation. So in order to do that, we need to do implicit differentiation. Now, can we write this in explicit form first and then find the derivative using explicit differentiation? Sure, we can. But this whole lesson is about practicing implicit differentiation, so we're not going to do that. So we're going to look at this as x squared plus y squared equals 1. We're going to take the derivative with respect to x on both sides. Since we have a sum here, we're going to be able to take the derivative of this separate from the derivative of this. So we have the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 1. Now we can take the derivative of each one. This one here would be explicit differentiation. I would just get 2x. Plus this one would be my implicit differentiation. We've done it a couple times now. 2y times dy dx. And this last one is just the derivative of a constant, which would be 0. So then what we're going to do is we're going to get the dy dx by itself. So we're going to move the 2x to the other side. So I'd have 2y times dy dx equals minus 2x. Then I divide the 2y, and I would get dy dx equals negative 2x over 2y. I could cancel these 2's, and so I get negative x over y. So dy dx equals negative x over y. Now, it asks us to find the slope of the tangent line at this point. And so now this point has to go into this derivative. And notice, when we do implicit differentiation, our derivative is dependent on both the x and the y value. Up to this point, we have seen derivatives where the answer is only dependent on x. So I don't know, like 3x squared plus 1. That's what our derivatives have looked like up to this point with explicit differentiation. The derivative is only dependent on the x value. So when we had to find the derivative at a point, we really only needed the x value for that point to find the slope there. But now when we do implicit differentiation, we need both the x and the y value for the point, which are in this case are both square root of 2 over 2. Well, so they're going to be the same here and here. So if I plug negative, because I still have the negative, square root of 2 over 2 over square root of 2 over 2, they're the same, and I'll get negative 1. So the slope of the tangent line is going to be negative 1 at this point, which would make sense if you look at this tangent line. It's going down from left to right, and that would have a slope of a negative value, in this case now negative 1. But we got there through this implicit differentiation. Here's another one. Find the equation of the tangent line of 3 times x squared plus y squared all squared equals 100xy at 3, 1. So this isn't just find the slope of the tangent line. This wants us to find the equation of the tangent line. But we need the slope first. So we still need to find dy dx first. And this is implicit. It's not a y equals equation. It's an implicit equation. So let's look at a couple things here first. Let's take the derivative with respect to x for both sides. So I have 3 times x squared plus y squared squared equals the derivative with respect to x of 100xy. Okay. So this is going to be a little tricky here, but let's look at this. We're taking the derivative with respect to x of this. I can't split this sum up because of this power here. So what I really have to do is apply the chain rule right away. This power is the outside. X squared plus y squared is the inside function. And so if I was going to take the derivative, this power would come out to the front. So I'd have 6. The new power would be 1. The inside would stay x squared plus y squared. And then I'd have to multiply by the derivative of the inside, which is x squared plus y squared. So I have to multiply by the derivative of that. And now I have to find the derivative of x squared plus y squared, which we just did in the previous example. Okay, I'll do that in a second. I'll move on. The other side of the equation looks a lot like an expression we've worked with a couple times now, a product. I can write this as 100x times y. So that's first function, second function. And if I apply the product rule, I would take the derivative of 100x first, which would be 100 times y, plus 100x times the derivative of y. That would be dy dx. Okay. So the only thing left to do is really this still derivative that's left here. And so I would have 6 times x squared plus y squared times, now I got to do this derivative. Well, since these are added together here, I could take the derivative of x squared and the derivative of y squared separately. We've done this enough now that I'm going to just go straight to it. So I have 2x plus 2y dy dx. And again, equals 100y plus 100x dy dx. Now, let's look at this. What we could do, there's two ways to do this. We want to know what dy dx equals. And we want to know what it equals at this point. What I could do is what we did in the previous two examples. I could try and get dy dx by itself here and here, start moving everything else to the other side, factor out the dy dx, and then once I have that, then I can plug the point in and find out what dy dx equals at this point. However, I should also be able to plug this point in for x and y here, and then get dy dx by itself. It shouldn't make a difference whether I get dy dx by itself first, then plug the point in, or plug the point in first, and then get dy dx by itself. So it will make my life easier to actually plug the point in first. So if I plug 3 and 1 in for x and y, I would have 6 times 9 plus 1 times 6 plus 2 dy dx equals 100 plus 300 dy dx. And I still have to get dy dx by itself, but at least now I'm dealing just mainly with number values that I have to isolate away from the dy dx. So this will be 6 times 10, so that'll be 60 times 6 plus 2 dy dx equals 100 plus 300 dy dx. Then this 60 is going to have to distribute in here because this dy dx that's sitting right here is kind of embedded inside this parenthesis, so I have to get it out by distributing this in first. So that will give me 360 plus 120 dy dx equals 100 plus 300 dy dx. Okay, now I got to get all the dy dx's together and everything else opposite. So I'll bring this dy dx over to this side of the equation by subtracting it. I'll bring this 100 over to this side by subtracting it. So 360 minus 100 would give me 260. Then if I subtract the 120 over here, that would give me 180 dy dx. Divide the 180 over to this side. So I would have dy dx equals 260 over 180, which would simplify into 13 over 9. So there is your derivative. That is the slope of the tangent line at this point. And again, I could have got dy dx by itself first here and then plug 3, 1 in. Either way, I should get 13 over 9. But that's not it, because that's not what the question said. It didn't say find the slope of the tangent line at 3, 1. It said find the equation of the tangent line. So now I need to use that slope. This is the slope. And I need to use this point and write the equation of the line. So if I use the point slope formula, y minus y1 equals m times x minus x1, my point was 3, 1. My slope was 13 over 9. And I would get y minus 1 equals 13 over 9 times x minus 3. I like to multiply this 9 to the other side of the equation. So 9 times y minus 1 equals 13 times x minus 3. Distribute out these parentheses. 9y minus 9 equals 13x minus 39. And then put it in standard form, x and y on the same side. So minus 13x plus 9y. Move this 9 to the other side. So add 9. So I would get 30. And there is my equation of the tangent line. Let's write that correctly. Tangent line at 3, 1. Okay? And so none of this is new. Okay? Really, the new part was the derivative component. So look at it. Depending on what the question asks, where can I plug this point in, and is there a point to plug in the first place? And sometimes you can simplify some of your computation by choosing to plug the point in earlier as opposed to later. All right, here's another one. Now this is going to be a very important example when you talk about inverse trigonometric functions in Calculus 2. We're not going to get into that right now. We're just going to look at it purely as an implicit equation that we need to find the derivative of. And it's not a y equals equation. It's actually it's an x equals equation, but in this case, that's still not what we want because we want to find the derivative of y with respect to x. If we wanted to find the derivative of x with respect to y, if we were looking at it that way, then this would be an explicit equation we could work with, but not getting into that. Okay, so let's just look at it as an implicit equation. What are we going to do? We want to find the derivative, dy dx. So I'm going to take the derivative with respect to x of both sides, sine y, and the derivative with respect to x on the other side. Okay? And so in the right-hand side, they're x's, so it's just basic explicit differentiation. I would get 1, the derivative of x with respect to x is 1. The right-hand side is where we have the the left-hand side is where we have the implicit part. And so this is a chain rule. Think of this as outside function and inside function. So if I take the derivative of the outside function first, I would have cosine. The inside function is going to stay the same. Then I have to multiply by the derivative of that inside function, so the derivative of y with respect to x is dy dx. Okay. And then the next step is to figure out what dy dx equals, so get dy dx by itself, so I'll move cosine y to the other side by dividing, so I would get dy dx equals 1 over cosine y, which is okay, but we could write that answer a different way. Okay? We could. And so we're going to use a little bit of trig identities to do that, in which case I'm going to use the Pythagorean identity, which says that sine squared theta plus cosine squared theta equals 1. And what I'm going to do is I'm going to solve this for theta, for cosine theta. And so I'll move the sine squared to the other side, so it tells me that cosine squared theta equals 1 minus sine squared theta. And then I can get rid of the square by taking the square root, so cosine theta equals the square root of 1 minus sine squared theta. And so whether it's a theta or it's a y, you could apply this identity, and so we'll apply it in terms of y, so we would have 1 over the square root of 1 minus sine squared y. Again, remembering that sine squared y equals sine of y all squared, we're going to use the fact that this tells us that sine of y is equal to x. So this should be x squared. So 1 over the square root of 1 minus x squared is another way of writing the derivative with respect to x, dy dx. Now, why would we do that? Right now, there's not really necessarily a great reason why we would do that. It's just writing the answer in terms of x's instead of in terms of y's. The real reason why I did that, to show you like this turns into this, is because we're going to need this when you talk about inverse trigonometric functions in Calculus 2. So it doesn't hurt to show you it now. But the real crux of this was right in here which is taking the derivative of an implicit equation and getting dy dx by itself, so you know what dy dx equals. All right, so here's a question. Doesn't look too different than one we did earlier. As far as the equation goes, x squared plus y squared equals 5 is instead of a unit circle, this is a radius 5 circle centered at the origin. But the big difference here is right here. That's asking us to find the second derivative. In order to find the second derivative, we have to find the first derivative. And so let's start there. So if we're going to find the derivative, dy dx first, we're going to take the derivative of both sides of the equation with respect to x, which again won't look too different than a previous example. And we're going to get a very similar answer. Take the derivative with respect to x of this piece separate from this because of the addition. So I would have 2x plus 2y dy dx equals the derivative with respect to x of 25, since it's a constant, would be 0. Move the 2x to the other side by subtracting, and then divide by the 2y, and we end up with dy dx equals negative x over y. Again, this subtracts over, we get negative 2x, divide this over here, we get 2y, cancel the 2's. It's the same example we did earlier. But now we want to take the derivative again. So how do you do that? Well, you take the derivative of the derivative. So I'm going to take the derivative with respect to x on both sides of this equation. Well, the derivative with respect to x of dy dx, okay, is the second derivative. And then I have to take the derivative with respect to x of negative x over y. So on the left-hand side, that is the second derivative. And on the right-hand side, well, I have to take the derivative of this quotient, therefore using the quotient rule. So if I was to use the quotient rule, I would take the derivative with respect to x of the numerator times the denominator minus the derivative with respect to x of the denominator times the numerator all over the denominator squared. That's your quotient rule. In which case, all right, these derivatives are not bad. So I would have the derivative of negative x would be negative 1, so that would give me negative y. Here's a negative, here's a negative, so I'm going to write that as plus x times the derivative of y with respect to x is dy dx over y squared. So that's what the second derivative equals. Now there's a little problem here. The little problem here is that the second derivative is equal to something that is based off of the first derivative. So we can do better here. We know that the first derivative is equal to this. So if I plug this in here, I could rewrite this as negative y plus x times negative x over y divided by y squared. And now I have an answer that has x's and y's in it only for the second derivative. But I would have to do some simplifying in this fraction, and I will. But ultimately, you see, we can do second derivative, we can do third derivative, we can do fourth derivative, and even if it's implicitly done, we can do that. And we had to because this derivative didn't just have x's in it, it had x's and y's in the value that it was equal to. And so we needed implicit differentiation again to do the second derivative. All right, let's take a couple of seconds to simplify this a little bit further, and then we'll wrap this up. So again, we have the second derivative is equal to, what did we say it was? It was negative y plus x times negative x over y over y squared. Okay. And so what I'm going to do is I'm going to have to multiply this in here. So we're going to have negative y plus negative x squared over y squared. Then I'm just going to treat this as its own thing. Problem here, I'm going to find a common denominator. Clearly it's y. So if I multiply this by y over y, so that I have the same denominator, what do I get? I get negative y squared minus x squared all over y squared. Well, you can write this as y squared over 1, so fraction divided by a fraction. We'd flip this and multiply, so actually this y squared multiplies into the denominator. So we would get negative y squared minus x squared over y cubed. And that's one way I could write the answer. Another way I could write the answer would be negative y squared plus x squared over y cubed. Again, that's what the second derivative is equal to. But we can actually do one better than that. And remember, the original equation was x squared plus y squared equals 25. That's where we started. And this is the second derivative of that. Well, if x squared plus y squared equals 25, then that's telling me that this equals 25. So I could do one better here and say this is actually the second derivative is equal to negative 25 over y cubed. And that would be the simplest way I could express the second derivative. So the whole point here is we can do second, third, fourth, fifth derivative implicitly. It gets a little bit more complicated. Sometimes the second derivative is written in terms of the first derivative. We could fill that in. Also, sometimes the original equation pops up in your answer. That doesn't happen a whole lot. That's pretty rare. And we could try and simplify a little bit more. But mainly, this is going to happen. Remember, that was dy dx. And rather than write the first derivative in terms of the second derivative in terms of the first derivative, we could fill in what the first derivative was there and just have an answer in terms of x and y. The fact that we were able to then get this x squared plus y squared out is not going to happen a whole lot. I mean, that's just coincidence with this example. But nonetheless, this is the simplest way to write the second derivative.